CS50.
This is CS50.
And this is CS50.
I'm so fancy. You already know I'm in the fast lane. From LA to Tokyo.
My favorite memory from CS50 was when I went to Puzzle Day.
Probably just the time spent working on problem sets with my friends and people who would eventually become my blockmates.
My best memory from CS50 is the hackathon.
The CS50 hackathon.
Hackathon. The hackathon.
The hackathon.
Rob Bowden. Just everything about him.
I'm so fancy. Can't you taste this gold? Remember my name. How to blow.
My favorite memory is when I was on stage and I played the prestigious role of a node in a linked list.
When we all got free Dropbox space and David was like, look under your seats, and it was like, space for everyone.
I'm so fancy. You already know I'm in the fast lane. From LA to Tokyo.
My advice for any incoming student would be to really work on the P sets with friends.
Office hours is very much your friend.
Make the most of your experience and meet as many people as you can.
Don't be afraid to ask for help.
Start the P sets earlier in the week.
I think the biggest thing is to take advantage of all the resources that CS50 has.
Go to office hours early in the week.
Definitely watch the shorts.
Don't procrastinate on your P sets.
Make sure you find a great group of people to work on P sets with. You can have a lot of fun and get work done together.
And don't be afraid to push yourself. Go for the hacker edition sometimes.
Write things on paper before you ever touch your computer.
CS50 is really great at providing ways to get help.
My one piece of advice is sleep. Has anybody said that? Sleep, for sure. It's easy not to do, but you gotta do it, I think.
I would say really be mentally prepared, because you're gonna love it.
I'm so fancy. Can't you taste this gold?
This is CS50.
This is CS50.
This is CS50.
This is CS50.
So this is CS50, and this is the end of week 0. And that was just some of CS50's staff who await you not only in sections and office hours, but also this coming weekend at CS50 Puzzle Day, which again is not at all about programming. Indeed, it's expected that you won't have to program anything, but rather solve problems using wits and friends alongside you. We will be joined by some of our friends at Facebook. If you register here, who for the past several years have actually been writing these challenges with us, and so they will be the ones ultimately running Puzzle Day, and so you will be challenged with precisely the kinds of things and problems that folks at Facebook like to think about. So that is tomorrow. Register at cs50.harvard.edu/register. Now, a word on a couple of staff in particular. This here is Ansel Duff, who was actually one of the co-authors of these binary bulbs that we saw on Wednesday, in addition to CS50's own Dan Bradley. Ansel Duff was also a former freshman advisee of mine 3 years ago, and he actually even built this lectern. He's gone on to do engineering sciences and more. Now, pictured here is actually Ansel 3 years ago at the CS50 hackathon when he borrowed one of our balloons, stuck it to his laptop, and for the next 12 some odd hours focused on his final project, taking breaks only to open bags of candy at the hackathon. But he went on more recently to spend this past summer with us, since CS50, for its staff and now students this semester, has its own 3D printer. And in a nutshell, a 3D printer is a device that looks quite like this. You fill it with a plastic spool that is melted down by the device, and you build things literally from nothing. You, much like a inkjet printer, you start spitting out little dots of plastic that form together to form whole objects. And so Ansel, for instance, earlier this summer has an iPhone 5, and he decided he really wanted to prop it up on his desk, but he didn't want to go out and buy something from the Apple Store or the like. So he sat down and started drawing something. He took a few measurements as to how thick and how wide his iPhone was. He drew this image here. He decided that he wanted it to have a 75-degree tilt as it was staring at him on his desk there. He then turned this, using software, into a 3D CAD model that looked a little something like this, and then he proceeded ultimately to actually create it. So in fact, if any of you here, perhaps in a row that I can throw to, haven't... there we have folks with iPhone 5s, and here we have 2 more. Wow, okay. All right. Now, not to be outdone, CS50's own Chang Gong also set out this summer to build quite a few things, and in fact, for reasons that are still unclear, has been slowly printing an army of elephants with articulating arms and trunks, a couple of which are actually here, if anyone would now like an elephant. All right. But what Cheng also did for us is he very kindly set up a camera, because that elephant, believe it or not, takes some 2.5 hours to print. Even the iPhone stand took 1.5 hours to print. And what Cheng went ahead and did was he set up a nice camera in front of this 3D printer, filmed for 1.5 hours as Ansel's design printed. We overlaid some sexy music to it in order to give you this look at how 3D printing works. And even though this is actually in plastic, realize if this is an area of interest to you academically, there are folks, among them Jennifer Lewis here at the School of Engineering, who are actually working on 3D printing, not plastic objects, but even increasingly biological materials to solve physiological problems for humans. But here is a little something from CS50. Anything like that in reality, but it's much cooler to watch it at that speed and with that sound. Now, on Wednesday, how did we first get here? We started talking about computer science, and we asked what it was. And it's about a number of things, and indeed there's so many different directions in which you can head after a course like CS50. In fact, if you picked up one of those unofficial guides to CS outside, the booklet that we've provided, whether you're thinking of taking just CS50, or maybe doing a secondary, or maybe even concentrating in CS, do flip through that, and you'll see a diagram toward the end that shows you the many different directions in CS that you can go off in. But for today, we'll focus again on really one of the fundamental views, perhaps, where you have inputs to problems, you have outputs from problems, and you have algorithms with which to create those outputs from those inputs. And one such example was, of course, this phone book here. And we used it as an example to go through an algorithm that was correct, and then another one that was correct but a little faster, and then another one that was a little more dramatic but fundamentally faster. Right? This phone book, we claimed, had about 1,000 pages. And how many times did I have to tear the phone book in half to find someone like Mike Smith maximally in a 1,000-page book? So 10, give or take. And so once I tore this thing in half, or simply more maturely divided it in half, it's only 10 pages out of 1,000. And if you extrapolate, a little unrealistically for a phone book, but if this phone book had some 4 billion pages in it, so completely unwieldy physically, how many times can you divide a 4 billion page phone book in half? So it's actually 32, give or take. And so 32 times only out of 4 billion pages can you find someone like Mike Smith. And that's efficiency. That's a good algorithm, dare say. But then we moved from that to try to formalize it. And I proposed this pseudocode. Pseudocode is not anything formal. It's not something you memorize. It's just something you express fairly intuitively using English or any language, really, that conveys your ideas succinctly. But what's key about pseudocode is that you try to anticipate all of the possible cases that might happen. And indeed, in this pseudocode, there were really 3 cases every time I divided the phone book. Mike might be to the left, Mike might be to the right, or he might be right on the page I'm on, or a 4th corner case, so to speak. A bad scenario might be one in which what is happening? Mike's just not in the phone book at all. And when programs crash, when Mac and PC software that you guys run on your computers sometimes hangs or quits unexpectedly, that generally means that some programmer, some human like you soon, just screwed up and made some mistake, maybe didn't anticipate that maybe there is no Mike Smith in the phone book. And if you don't actually write code to handle situations like that, generally unpredictable things can happen. Your machine can freeze, it can reboot, the program can quit. And so all of these stupidities that you've may encountered in your actual life just using computers will increasingly be just explained away by this intuition and this understanding of what is actually going on underneath the hood. Now let's try to take a look at a more general problem. Rather than take attendance in a place like this, which would be quite slow to do, 1, 2, 3, 4, or maybe 2, 4, 6, 8, let's focus instead on how we might formalize the algorithm or the process by which we could take attendance. And along the way, let's start to apply some nomenclature that we'll use today when we actually start programming in a language. So I give you now a 4-minute video that we put together with our friends from TED, the organization whereby we supplied a script and they brought their animators to bear and actually created a 2D animation of what an algorithm is. If we could dim the lights.
what's an algorithm? In computer science, an algorithm is a set of instructions for solving some problem, step by step. Typically, algorithms are executed by computers, but we humans have algorithms as well. For instance, how would you go about counting the number of people in a room? Well, if you're like me, you'd probably point at each person, one at a time, and count up from 0. 1, 2, 3, 4, and so forth. Well, that's an algorithm. In fact, let's try to express it a bit more formally in pseudocode, English-like syntax that resembles a programming language. Let n equal 0. For each person in room, set n equal to n plus 1. How to interpret this pseudocode? Well, line 1 declares, so to speak, a variable called n and initializes its value to 0. This just means that at the beginning of our algorithm, the thing with which we're counting has a value of 0. After all, before we start counting, we haven't counted anything yet. Calling this variable n is just a convention. I could have called it most anything. Now, line 2 demarks the start of a loop, a sequence of steps that will repeat some number of times. So in our example, the step we're taking is counting people in the room. Beneath line 2 is line 3, which describes exactly how we'll go about counting. The indentation implies that it's line 3 that will repeat. So what the pseudocode is saying is that after starting at 0, for each person in the room, we'll increase n by 1. Now, is this algorithm correct? Well, let's bang on it a bit. Does it work if there are 2 people in the room? Let's see. In line 1, we initialize n to 0. For each of these 2 people, we then increment n by 1. So on the first trip through the loop, we update n from 0 to 1. On the second trip through that same loop, we update n from 1 to 2. And so, by this algorithm's end, n is 2, which indeed matches the number of people in the room. So far, so good. How about a corner case, though? Suppose that there are 0 people in the room, besides me, who's doing the counting. In line 1, we again initialize n to 0. This time, though, line 3 doesn't execute at all, since there isn't a person in the room, and so n remains 0, which indeed matches the number of people in the room. Pretty simple, right? But counting people one at a time is pretty inefficient too, no? Surely we can do better. Why not count 2 people at a time? Instead of counting 1, 2, 3, 4, 5, 6, 7, 8, and so forth, why not count 2, 4, 6, 8, and so on? It even sounds faster, and it surely is. Let's express this optimization in pseudocode. Let n equal 0. For each pair of people in room, set n equal to n plus 2. Pretty simple change, right? Rather than count people one at a time, we instead count them 2 at a time. This algorithm does twice as fast as the last. But is it correct? Let's see. Does it work if there are 2 people in the room? In line 1, we initialize n to 0. For that one pair of people, we then increment n by 2. And so by this algorithm's end, n is 2, which indeed matches the number of people in the room. Suppose next that there are 0 people in the room. In line 1, we initialize n to 0. As before, line 3 doesn't execute at all, since there aren't any pairs of people in the room. And so n remains 0, which indeed matches the number of people in the room. But what if there are 3 people in the room? How does this algorithm fare? Let's see. In line 1, we initialize n to 0. For a pair of those people, we then increment n by 2. But then what? There isn't another full pair of people in the room, so line 2 no longer applies. And so by this algorithm's end, n is still 2, which isn't correct. Indeed, this algorithm is said to be buggy because it has a mistake. Let's redress with some new pseudocode. Let n equal 0. For each pair of people in room, set n equal to n plus 2. If one person remains unpaired, set n equal to n plus 1. To solve this particular problem, we've introduced in line 4 a condition, otherwise known as a branch, that only executes if there's one person we could not pair with another. And so now, whether there's 1 or 3 or any odd number of people in the room, this algorithm will now count them. Can we do even better? Well, we could count in 3s or 4s or even 5s and 10s, but beyond that it's going to get a little bit difficult to point. At the end of the day, whether executed by computers or humans, algorithms are just a set of instructions with which to solve problems. These were just 3. What problem would you solve with an algorithm?
So deliberately, a very simple program, a very simple algorithm for achieving something very simple, counting the number of people in the room. But let's tease apart some of the representative features here that are actually going to be useful even when implementing the most complex of software. So for instance, in this first line, we had what we called a variable. And from algebra, you're generally familiar with using x and y and z sometimes and so forth. But in programming, Variables are still, at the end of the day, very similar to that, but it's perhaps simpler to think of a variable as just a container. And in fact, it's some number of bits implemented somehow in your hard disk or in your computer's memory, but more on that in the future. It's just a container. And if you say something like let n equal 0, well, that's like calling this glass bowl here n, just an arbitrary name, and putting nothing in it initially. So the value of this bowl right now is 0. And of course, if you proceed in a subsequent line to actually increment some line of code, as in this third line here, by 1, that's like saying, all right, what's the current value of n? It's 0. Plus 1, put something like a ping pong ball in here, and now the value of this variable is quite simply 1. And you could very quickly extrapolate that now it's 2, now it's 3, and so on. So that's all a variable is. It's a piece of storage to actually store some data. For now, it's a ping pong ball. There, it's a number, but it could be words in a dictionary, like the spell checker I alluded to on Wednesday for one of last year's problem sets. Now, another key idea that similarly is pretty intuitive, I would claim, is that of a loop. And the loop in the process of counting everyone is, of course, doing the same thing again and again, either one at a time or two at a time. And you can express this in English or pseudocode in any number of ways, but using this preposition for is a very common way of doing that. For each person in the room, do this again and again. And the fact that it's indented, line 3, just means that what you're supposed to do is the stuff that's indented below line 2 itself. Just a human convention, but a common one, as we'll see, in actual higher level programming languages. Now, a little more interesting is when you get a corner case. For instance, a corner case was when there were 3 people, or 5, or 7, or any odd number of people in the room, because doing that by 2s breaks eventually, because you're going to miss someone, either at the very beginning or the very end, depending on how you do it. And so now I have this branch or condition. If one person remains, then go ahead and handle that one lonesome person who didn't get paired with someone else. So that's what we would call a condition or a branch. Now, pseudocode more generally can be written to solve any number of problems. And what I thought we'd do here is take a moment to invite, shall we say, CS50's own Rob Bowden on stage to be joined by 2 volunteers who have no idea what awaits. So, a hand went down as soon as I said that. How about you on the end here? Come on up. And how about from farther away? How about way in the back row? Come on up with your hand up. All right, and what's your name? Anita. Okay, nice to meet you. Let me introduce you to Rob Bowden. This is Anita. And what is your name? Kirsten. Kirsten, come on up and meet Rob Bowden and Anita. Nice to meet you.
Nice to meet you.
All right, Rob. Anita, and your several hundred classmates. So now let me go ahead and pull up just a simple program here on Mac OS that'll let me actually jot some notes down. And if you guys want to each take a position at one of those stools there, let me go ahead and start a list of pseudocode, if you will. And what I want to do here ultimately is type for you some instructions that our audience members are actually going to recite for us. Let me go ahead and just change this to a numbered list to match what we were doing up there. And what I'm going to do, with your help, is write a program in pseudocode with which these guys are going to implement a peanut butter and jelly sandwich. So it's perhaps apropos to show some things some of you might have seen on the internet for just a brief annoying moment.
It's peanut butter jelly time. Peanut butter jelly time. Peanut butter jelly time. Where you at? Where you at? Where you at? Where you at? There you go. There you go. There you go. There you go. Peanut butter jelly. Peanut butter jelly. Peanut butter jelly. Peanut butter jelly. Do the peanut butter jelly. Peanut butter jelly. Peanut butter jelly with a baseball bat. Peanut butter jelly. Peanut butter jelly. Peanut butter jelly with a baseball bat. Now where you at?
Okay, that's enough of that. So here, meanwhile, I have a pair of Google glasses, which we'll put on CS50's own Rob Bowden to see the world through his eyes, and we'll do our best in post-production to actually weave the footage of what Rob is seeing now into this actual lecture video with our 2 volunteers beside him. So what I'm going to do is I'll be the typist. We have the goal here of actually writing a program with which to make ultimately a peanut butter and jelly sandwich, but these 3 are going to behave as though they are computers. And computers, at the end of the day, are actually pretty dumb devices. They're super fast, but they can only do literally what they are told. You can't just say make a peanut butter and jelly sandwich. You have to program them to do that. You have to tell them with precision what to do, lest things go horribly and hopefully amusingly awry. So with that said, we need one call out from the audience for what should step 1 be if the goal here is to make a peanut butter and jelly sandwich. Yes? Open the bag of bread. So if the three contestants would like to proceed to do that literally, open the bag of bread. So let's work on that. All right. So step 2. Let's take this further. Yeah, in the front. What's that? Remove the bread. Similarly succinct. Thank you. Okay, that's it. Okay, so step 2 is going to be remove the bread. All right, someone want to write us a longer sentence? Someone else. A little more committal. No, nothing now. Yes? Place 2 slices next to each other. Place 2 slices next to each other. Step 4. Yes? Wait, say that again? And put it gently next to the peanut butter. Okay, progress. Step 5, excellent. Yes. Pick up knife. Okay, step 6, yeah. Hold knife by the handle. Hold knife by the handle. Step 7, yes. Put knife in, I heard put knife in peanut butter and take as little out as possible. By the way, remove paper first. All right, step 9. Step 9. Step 9. We haven't actually made a sandwich yet. Yes? Using knife in peanut butter, apply peanut butter on said bread. All right, step 10. Step 10. Yes? Step 11. Step 11. Step 11. Come on, yeah, right there. Carefully pick up jelly. Okay, and then another hand was up. Right behind you, yeah. In blue. From jelly. And there. Paper from jelly. Step 14. We're almost there, yes.
Invert jelly bottle before everything falls out.
Invert jelly bottle before jelly falls out. Step 15. Replace the cap. Step 16. Yeah? Say that again? Off your jelly? So really, go. Oops. Come on. Replace the cap. Put cap. You said remove cap from jelly. Feel like we're in a bit of a loop. Step 17, yes. Say that again. Go back to step. Remove cap from peanut butter. Yes? Drop all the jelly on the bread. We're almost there. Step 19. Jelly. Why don't we get one more step to take this home? One more step, and then we'll serve sandwiches. Yes? While any sandwich remains, let's indent this, eat. All right, thank you to our volunteers here. We have some nice parting gifts for each of you. Your own peanut butter, jelly, and bread to bring back home. Thank you. So, this is, of course, a ridiculous example, right? But it does kind of reveal how we humans just take clarity for granted, and the fact that in talking to another human, he or she just kind of knows what you mean. Computers are not going to know what you mean. Even when using, as we're about to do today, programming something in Scratch, a drag and drop puzzle piece style language, even designed for young children, you have to be so explicit and so literal with what you want your program to do. Now, ultimately, we're going to be programming not in pseudocode, English-like syntax, but code, or more properly, source code. Source code is just the fancy way for describing code that you actually write with a keyboard that's not in English per se. It's in C or Java or C++ or something like that, as we'll soon see. And in fact, just to scare a few of you, at first glance, this is a program written in a language called C. But to unscare a few of you, you will completely understand what's going on come next Monday when it comes to something like this. Frankly, this is an older language. It's fairly arcane, but it's representative of a lot of languages these days that have lots of parentheses and curly braces and quote marks and semicolons and a lot of this syntactic stuff that is not at all intellectually interesting. And indeed, it's an utter distraction from the very simple ideas that are staring us in the face. This program, as you might just guess, prints to someone's computer screen the words hello, comma, world. That's it. So clearly there's a lot of stuff that's getting in the way of some obviousness there, but it's going to very quickly slip away and be completely intuitive. Indeed, what we're going to do today is distill this fairly complex-looking program, which again you'll come to understand quickly, but to something much simpler. Let's just say what we mean. Let's draw a picture of what we mean by way of these puzzle pieces here. So this is a programming language known as Scratch. It was developed by MIT's Media Lab, and what you'll see in problem set 0, which will be released later tonight, we'll have you go to this URL here, scratch.mit.edu, and they have a web-based interface via which you will write your first programs, or those of you with prior experience, your second programs, but in an environment that's probably a little unfamiliar, and that will push you to create something using this very visual environment. Now, what I'm going to do here is open up the program itself. It exists not only as a web browser, but also as a downloadable program so that you can actually use it if you don't have internet access. And I'm going to do that in here in Sanders just in case the Wi-Fi doesn't cooperate super well. And what I'm going to do is point out a few features of this program. So to be clear, I have just double-clicked an icon on my desktop, or equivalently gone to scratch.mit.edu, and it's pulled up this window. This is a programming environment. It's a piece of software that some of our friends at MIT wrote that lets us and you write programs in a language called Scratch. Now, this happens to be a cat who's also named Scratch, and this is his world in which he lives. This is his stage, so to speak, that rectangle in the top left-hand corner. And he doesn't have to look like a cat. You can make him look like anything, and you can have many such sprites or characters in a program. Meanwhile, over here on the far right is a big blank slate. And this is where, in a moment, we are going to start programming by dragging and dropping these graphical puzzle pieces that are right here in the middle. And there's way more of them than we'll spend time on here in class because you'll find that they're all fairly intuitive. Again, it's designed for children, but we use it to tease apart some of those fundamental ideas of variables, loops, conditions, and soon things like functions and events and threads and other fancy things we'll get to before long to actually create something from scratch, pun intended. Now, what I'm going to do here is click on not motion, but control. And this is just a categorization of here, and I see a different color set of blocks. But notice a few familiar words, if and else if and repeat. And you can probably guess that that's reminiscent of the branch or the conditions we saw and even the looping construct. So we have similar blocks here. But the most interesting one is this one here. When this green flag is clicked, this, for those with prior programming experience, is equivalent to like a main function. But for those unfamiliar, this is the puzzle piece that will kickstart our entire program. It literally means when I go in this program and click a green flag, which you can see up here in the top left-hand corner of the UI, so see the green flag next to the red stop sign, when I click that, my program is going to run. Now I'm going to do something super simple with Scratch. I'm going to go ahead and go to the looks panel here, where I have a bunch of purple puzzle pieces, and I'm going to go ahead and do something super simple like say, and then notice this text in the white box is editable. I'm going to say hello world, just like we did in that textual version a moment ago. And now if I go and click this green flag, I have now programmed. Right? It's not a particularly interesting program, but I made the computer do something. I started a program, and it did what I told it to do. Now I can continue to drag and drop more and more of these puzzle pieces, and they're going to interlock, but let's slap some terminology on here that we'll see recurring throughout the course and really throughout computer science and programming more generally. This say block in purple, let's just start calling it a statement. It's like a statement of fact. Do this. So it's kind of a category of instructions that you might feed a computer as part of a program or an algorithm. And to be clear, you've probably taken for granted that you have programs on your computer, and they're kind of algorithms, but a program is really a bunch of algorithms that some humans wrote, they packaged it up, and they sold it to you, or they posted it on a website for you to download. So a program is just a bunch of zeros and ones that somehow humans created, and those patterns of zeros and ones represent things ultimately like say hello world, or play this music, or play this video, or send an email. But we'll come back in way more detail what a program is when you yourself write them. Here's another statement. Wait for 1 second. I didn't use this yet, but if I want my program just to pause for a moment to do something, I can tell it to do so. Wait 1 second. Now, another one might be play sound. So this is unique to Scratch. It has the ability to play sounds. So a statement I might use is here, play sound. Meanwhile, Boolean expression. So this is a fancier word named after just a guy named Mr. Boole, and this is all about a question. True or false, is the mouse down? A Boolean expression is just some expression in English that is either true or false, either on or off, either 1 or 0. You can think of it in any number of ways, but it's either true or it is false ultimately. So mouse down question mark, that would be a Boolean expression. And you can think of others perhaps. For instance, is the left number less than the right number? That too would be a Boolean expression. Less than is a Boolean expression. This one too, touching mouse pointer. I'm not sure why they called it mouse pointer. It just means is the cursor, is the arrow on the screen touching the cat, for instance, or some other aspect of the screen. And it's a question again, and that denotes a Boolean expression, something that you might want to use in a condition. So we'll come to that in just a moment. You can and things together. So if you want to check if this is the case and that is the case, you can use an and block like this. And here's that condition. Notice the shape of the little opening in the top of this yellow puzzle piece. It's reminiscent of the shape that we just saw a moment ago. Each of these Boolean expressions have these pointed edges on the left and right. And that's because the MIT folks decided that by visually conveying shapes, you can kind of help people, students and children alike, to kind of fill in the blanks literally. Now that puzzle, that opening is a little small, and as we'll see in the program in Scratch, it'll grow to fit, but it will maintain its shape ultimately. So a condition lets you decide, should I do something or not? A Boolean expression is the actual question you're using to decide, do I go to the left or do I go to the right when I encounter this so-called fork in the road? You can have two branches. If something is true, do this, else go that way. Or you can just do nothing at all, as this block implied. Similarly, we can nest these things. So if you want a triple fork in the road, either do this or that, you can just nest these things together. And it starts to get a little ugly eventually, for sure, but the logic is still the same. You can literally read this top to bottom, and it says what it means. If this is true, do this, else if, else. A loop doesn't get simpler in Scratch. Forever, do the following. Now, you might not think you can do much because there's not much space between the top and the bottom of this puzzle piece opening, but you'll see Scratch is going to grow to fit as many puzzle pieces as you want to cram in there. Another loop might be expressed with repeat. If you know in advance, I want to do something 10 times, you can just tell Scratch to do something 10 times. And meanwhile, we can have variables. So here's an arbitrary one. It's orange in this case. And this is a whirlwind tour. Again, you'll find this very accessible once you start pointing and clicking. I've named my variable n, but I could have named it anything I want. And I'm setting it here in this arbitrary example to 0. Now, seeing a program like Hello World is not all that compelling. So let's actually open up something that a former student made. Let me go ahead and open up, for instance, this one here, for which I would love to have a volunteer. All right, how about, let's go a little farther. Yes, come on up. What's your name? Abby. Abby, come on up. So have you ever played this game before? No. All right, David, nice to meet you. Come on over. And what is your programming background, if any?
I have learned some C++.
You've learned some C++, and what is your game playing background?
Not a lot.
Okay, so we'll take that. So here's how the game's going to work. I'm going to go ahead and click the green flag, which is up here at the top right. Now, your predecessor in the class has given you some instructions here. And in just a moment, it says space to begin. So go ahead and hit the space bar. Pikachu! And the goal is to catch the food, as depicted there on the left, and to not catch the other. Oh, well, thank you for playing. We have here a little parting gift here for you. We have CS50 stress balls if you'd like to choose. All right, good to meet you. Thank you for coming and challenging. So we have more stress balls. So let's do one more example to motivate a volunteer. All right, how about, it's right here in front. What's your name? Philip. Philip, come on up, Philip. So Philip is going to be challenged with another game that one of your predecessors wrote as part of problem set 0 called Ivy's Hardest Game. And we'll see in just a moment what's meant by this. Philip, nice to meet you. What is your background?
Done a lot of coding, done a lot of gaming too.
Okay, got a lot of gaming too, and have you played this game before?
No.
All right, so here we go. I'm going to go ahead and click the green flag.
Can't touch this. Can't touch this. Can't touch this. Can't touch this. My music hits me so hard, makes me say, oh my Lord, thank you for blessing me. What am I to rhyme and do like this is good? When you know you're down, a super dope homeboy from the Oak Town, and I'm known as such, and this is a beat you can't touch. I told you, homeboy, you can't touch this. Yeah, that's how we living, and you know you can't touch this. Look in my eyes, man, you can't touch this. Yo, let me bust the funky lyrics. Fresh new kicks and bands, you got it like that. Now you know you wanna dance, so move out of your seat and get a fire girl and catch this beat while it's rolling. Hold on, pump a little bit and let them know what's going on like that. Like that. Hold on a minute, just fall on back, let them know that you're too much. And this is a beat they can't touch. Yo, I told you can't touch this. Why you standing there, man? You can't touch this. Yo, sound the bell, school is in, sucker. You can't touch this. Give me a song, a rhythm, make them sweat. That's what I'm giving them now. They know, they talk about the hammer, they're talking about a show that's hot and tight. Singers are sweating so fast, I'm a whiteboard tape. To learn what it's gonna take in the 90s to run the charts. Legit, either work hard or you might as well quit. That's word, because you know you can't touch this. You can't touch this. Break it down.
All right, congratulations. We will post that online later so that you can procrastinate with it as well. Princeton comes up next after that. So now let's actually proceed to start from scratch, so to speak, and actually build up until we can tease apart some of these ideas and get to something even more complex by the end. I'm going to go over here, and I'm going to go ahead and create a new file. So again, the problem set will walk you through some of these steps, but all I did was go to the File menu, and I said New. So much like Microsoft Word or any program like that. And let's go ahead now, and we implemented Hello World a moment ago, but let's do something a little cuter. I'm going to go up to Events, and I'm going to do When Green Flag Clicked. And then I'm going to use, shall we say, a branch. So I'm going to use an if condition. And notice how as soon as I get close to it, it kind of wants to snap together. So I let go, and it snaps together. And now I can do something interesting. If I scroll through here, I'm going to see a whole bunch of blocks. If I go to Data, let me zoom in. There's something about variables. If I go to Motion, you can apparently turn things around. If I go to Operators, well, this is interesting. I can pick a random number. So let me do something with only some probability, just because. I'm going to go ahead and drag this puzzle piece. This is that less than block. So it's just, is this number less than that one? But I don't want to hard-code a number, because that'd be pretty pointless. So I'm going to drag this piece here, and notice how it snaps in. And now let me go ahead and say, if the number that's picked randomly is less than 6, do the following. Now, why less than 6? What probability is this effectively going to give me, just intuitively? 50%, right? If the number that's guessed randomly between 1 and 10 is less than 6, clearly it's 1, 2, 3, 4, or 5, and so that's going to give me a 50% probability of what happening. Well, let's do something like this. Play sound meow. And notice again, the puzzle piece grows to fit so long as the shapes match. That's what's important. Let me go over to Scratch here and click play. Nothing happened. Was that a bug? No, not necessarily. It could just be that a bigger number was chosen, so let's do it again. Nothing. There it is. Again. No. So if you've ever played a game, of course, where stuff is kind of happening randomly, like the bad guys are coming or not coming onto the screen, or things are falling or not falling, that's just because something super simple like this is happening. Pick a random number, and if it's less than some value, maybe do this or maybe do that. So we can incorporate that into a condition. Let's do something different. Let me throw that away, and you can get rid of stuff by just dragging it off to the left and letting go. Let me go ahead and do a forever block and very quickly do something annoying. Let me go ahead and say play sound meow, but I don't want this to be too annoying, so let me grab this block, wait 1 second, and notice there's no more room for it, but if you go close enough, it wants to go there, so I let go, and it will grow to fill the block. So now this is a loop. I'm literally doing this forever. Again and again. That is just not natural sounding. Let me go ahead and change this not 1 second to 2 seconds and hit enter. And what's nice about Scratch is that you can program interactively. Make a change, maybe hit enter or play again, and it will just keep going. Well, now why don't we do something a little cuter? Rather than do everything from scratch, let me go ahead and open up an advance-made one that I pre-baked called Pet the Cat. And we'll post all of these files online, and Problem Set 0 will tell you how to access them and open them up. And notice this is pretty simple. But in advance, I seem to have grabbed a forever block. So I've got a loop. And then I've got an if condition. I've got a Boolean expression. So in English, just glancing at this, especially if you've never programmed before, just intuitively, what is this going to do, this program? It's going to let, if you pet the cat, it's going to meow, right? Because forever, I'm checking, is the mouse pointer touching the cat? So to be clear, and I didn't say this before, all of these puzzle pieces and the script that we have combined them into, so to speak, a script is synonymous with program, really, belongs to this cat. And the reason is because notice how this same cat here is highlighted. Down here, you can create a second cat or a dog or really anything you want graphically. You can import something from Photoshop or the like and integrate something if you want to make it for a project. And what you'll find ultimately is that you can add scripts, add puzzle pieces to individual characters. So these all belong to this particular cat. So now if I go ahead and play this program, nothing's happening, but it is running. Right? The program is in this forever loop, kind of waiting for what to happen. To pet the cat. So if I move my mouse toward him, so now I'm petting the cat. Meanwhile, we can have a double branch. Let me go ahead and open up Don't Pet the Cat. We'll post this online as well. This is a little more complex, but without saying, you can kind of guess perhaps what's going to happen. Cat's meowing, having a grand old time. But program's, of course, called Don't Pet the Cat, so clearly I want to pet the cat. Don't pet the cat. Now let's take a look at another example here. This one will be called hi, 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 for reasons that will be clear, because as soon as I run this thing, it's very easy to write annoying Scratch programs. Now we won't go into great detail with all of these, but notice there's a couple of new features here. There's a variable called muted, and then there's a bunch of conditions. And for now, let me just tease you by saying that if this guy gets too annoying, I can hit the space bar, and he stops. Because the role being played by these two scripts is as follows. One of them is doing the barking every few seconds. The other one is just waiting for me to hit the space bar, and if I do hit the space bar, it's going to change the state of this variable, the value of this variable that's apparently called muted. I didn't call it something boring like n. I called it an English word, muted, from 1 to 0 or 0 to 1, from true to false or false to true. And so you can actually see now that you can have two scripts, two programs running simultaneously, and both of them might be sitting in a loop doing something, waiting for the human to do something like hitting the space bar. And now he's on his way again. So what else might we do with these examples? Well, let's go ahead and do an example with counting sheep. We'll continue this along the lines here of let's open up the sheep example. And notice, much like before, this one thankfully is a little less annoying. Once I hit play here, oh no, this is annoying. He is going to baa with some probability. Let's play this again. The only difference is we've changed the costume, so to speak, and we're having him say what that actual number is. Well, let's go ahead and take this one step further, and let me tease you with one other feature here. Let's go ahead and open up a program called Threads. So much like you can have one sprite having multiple scripts, you can have two sprites, a bird and a cat, each having their own script, and each of them can operate simultaneously. If you've ever heard the word multi-threading, a computer is multi-threaded, it means it can do multiple things at once, and indeed so can Scratch. And now notice, the bird is kind of dumb. It's just doing things randomly, bouncing off the screen. Clearly, the cat has been programmed to kind of have heat-seeking capabilities to home in on the bird, because he's always pointing at him until finally he catches the actual bird. So I won't dwell on the details here, but you can kind of glimpse the same shapes, some if conditions, some variables, maybe some loops are ultimately doing the same thing. Now let me go ahead and open up something else altogether to tease some of you, particularly those more comfortable, what you can actually do with this. I'm going to go ahead and open up button here, and this is a super simple seeming program, but watch what happens when I open this version of it here in the browser, scratch.mit.edu, and when I click this big red button, notice what happens. So what's going on here? There's actually a lot more complexity going on underneath the hood, even though I've implemented this, or frankly, Dan Bradley has implemented this so simply. He has designed a custom Scratch puzzle piece known as a Scratch extension. He called it Toggle, and what Toggle does is it sends a message over the internet, and that message itself looks a little cryptic, but this too you'll understand by term's end. The message he's actually sending looks a little something like this. It's just text, cryptic, you'll understand it by the time we get to problem set 7. It's just sending a textual message over the internet to a server, and that server is ultimately talking to this light bulb, which has one of those fancy light bulbs in it that itself is talking to the Wi-Fi in the network here, or a local device down here, and ultimately it's actually turning that light on and off. But we can do more interesting things still. Notice what Dan also did for us. He made multiple sprites, each of which has a script waiting for a click, and if I click red, it goes red. If I click blue, it goes bluish, green, yellow, orange, and all of this is happening by going way out onto the internet, back down here to the light bulb, on and off. And if you can believe it, and this is perhaps one of the most complex Scratch projects someone has implemented, he did it, in fairness, in a day. And that was the challenge we threw down to Dan when we saw we have binary bulbs, we have Scratch, how can we combine them? And indeed, this is absolutely something anyone in this room could do by semester's end, is he re-implemented binary bulbs using the same interface that was on our iPad on Wednesday, so that now if I actually click the plus over here, we have 1, 2, 3. I can hit the 16 and turn that one on. 128, and so forth. Now, if that alone hasn't blown your mind, you can do things far sort of more accessible, not involving any hardware, certainly, just things on the screen itself. And indeed, what most students end up doing is some kind of game, some piece of artistic work, or some kind of interactive animation. And I will say one of our favorites has been this one, and I thought if we could dim the lights, we'll take a glimpse at this final Scratch project in conclusion. But what you should keep in mind, as I can tease you with one last detail, sectioning will begin next week. Office hours will begin next week. Problem Set 0 will be posted at cs50.harvard.edu later today, and you will be greeted in Problem Set 0 to CS50's own Zamila Chan, who guides most of our walkthroughs. These are embedded videos in the problem sets that will hold your hand through a lot of the initial setup and through many of the possible design decisions. So if you've ever had that emotion when picking up a homework assignment and wondering, where do I begin? She will have that answer for you. And now, a final program from one of your predecessors in answer to the question, what does the fox say?
Dog goes woof, cat goes meow, bird goes tweet, and mouse goes squeak. Cow goes moo, frog goes crow, and the elephant goes toot. Ducks say quack, and fish go blub, and the seal goes ow, ow, ow. But there's one sound that no one knows. What does the fox say?
That's it for CS50. We will see you at Puzzle Day and on Monday.
And now, Deep Thoughts by Davin Farnham.
Today, I got hit in the face with a phone book. Confusing as I'm at home, watching online.